lockdown reasons. It was not so easy to get lecturers, but I am happy that nevertheless we managed. But I am particularly happy and honored to welcome the first speaker in the series, who is Aleksander Mądry, who is now professor at MIT, but also officially visiting our department. But unfortunately, we cannot meet every day and talk in Kubush or in club because of this lockdown situation. But nevertheless, well, Aleksander is with us during this year. Well, Aleksander Mądry is a researcher whose research interest is very large and who I think has a holistic perspective on computer science. He started with work on algorithms, and the list of best papers he had is really impressive. Stock, Fox twice, I think, Soda, and so other academic awards like Pressburger Award. But now Aleksander is interested in machine learning and the relations of theory and practice. And so I think that we all will enormously profit from his lecture. So let me also add that he will collaborate here with Maciej Statkiewicz and Piotr Wygotsky with the group of MIM Solution who will run tutorials. So many thanks, Aleksander, that you found time and interest to give this series of lectures, and welcome.
Great, thank you, Damian. Thank you, everyone. And yeah, so it's a pleasure to give this lecture. And I also really want to thank Maciej and Piotr for stepping up and helping with the tutorials and essentially making everything happen. So yeah, it's always fun to visit Warsaw. I would prefer it was under different condition, but here we are. Yeah, as Damian said, actually, to those of you who know me a bit longer, yeah, it might be a little bit surprised what am I doing here talking about machine learning, but there is a reason, and kind of very roughly speaking is kind of, machine learning currently is in a very interesting state where there are some very inspiring and developments that kind of, everyone is excited about, but there's not that much understanding of why it works, how it should and how it should work the way that we essentially when we actually would like in some ways there is a question of what we would like to happen, and then and there is a question of what's happening right now, and these two things do not exactly match, and that will be kind of a focus of this lecture to show that from one particular perspective, the robustness perspectives, things are not where we would like them to do. And I want to give you an insight into the problems, but also in some of the current attempts, ways of trying to make sense of the landscape and trying to make a difference and trying to improve on this axis. And also I want to mention that some of the materials that we are using here actually, they are derived from materials prepared by two of my excellent students, Dimitri Tsipras and Shibani Santurkar. Okay, and by the way, the order should be flipped. I just, I'm not good at alphabet apparently. Anyway, let's get started. So yeah, so why are we here? Well, we are all here because we are all incredibly excited about what machine learning has done. But if you really think about it, it's what it promises. I think there are some impressive things it has done, but in the end, what really excites us is kind of what will happen next. Right, and in particular, we don't as much as we AlphaGo, or we like the progress in image classification. What we really envision is how this technology kind of gets deployed in the real world, and kind of where it changes essentially things that we have seen in science fiction that and seems science fiction just 10 years ago now to seem to be within our grasp, and kind of we are all looking forward to making this happen. Okay, and kind of, so this is where we would like to go. And the obvious question would be, okay, so, if you look at the kind of technology we have right now, the ML technology that we have right now, is it actually ready for this broad real world, deployment? And, if you look at the news, you might think, yeah, that we are getting there. One of the definitely very exciting and interesting development is, the Tesla autopilot mode and other self-driving cars. So this is one actually of quite early demos of Tesla, and it's like super impressive. Yes, like you have this car driving around by itself, understanding the scene, and essentially like, everything looks like a science fiction movie, except this is a reality. So this kind of would make you believe that, we are almost there, and that's definitely what Elon Musk would like you to believe. However, there are also other videos that maybe are not as widely circulated, but very much also real. So this is just one example from, this is just from June this year, where, on a highway, there was an overturned truck. And essentially it was a Tesla in self-driving, like in the autopilot mode driving, and essentially just drove into this truck without even trying to brake. Well, I guess it started to brake when the driver realized that, what's going on. But essentially, like, Teslas tend to be quite safe, except sometimes they aren't. And if you look on YouTube, you will find plenty of videos where Tesla do things that we don't want them to actually do. So clearly there is something amiss here. And essentially, like, that's the question. Okay, so like, and that's the question that I will try to shed some light on today in the talk. Is like, what's going on? Like, where this brittleness, this not robustness, might be coming from. Okay, and the point of start here is, something that is undeniably, the home run of machine learning in general, but in particular, prevailing approach to modern machine learning used today called deep learning, namely the ImageNet challenge. So what is ImageNet? So ImageNet is this kind of, very large collection of images, like over 1 million of them. And kind of the idea there is that, like, each of these images has one of the 1,000 possible classes assigned to it, like kind of as corresponding to, essentially what is, like, the intention is that this should be what is on this image, like one of these 1,000 classes. And then your goal is, to train on, large subset of these images, which is the training set, and then kind of infer, train a model that then when facing the withheld, the rest withheld images, it's able to tell what the correct label for that image is based on what it learned from the training image. Okay, so that's kind of the most prototypical supervised machine learning task. And again, indeed, so there was this benchmark, and actually, like, usually what people started to measure was this kind of top 5 accuracy. So essentially, like, whenever you are confronted with an image, you actually don't have to return one class. You can return up to 5 classes that you see that, like, might be the possible correct classification for this image. And if one of them is correct, then this counts as a success. Otherwise, it counts as an error. And what you see on this plot is essentially the progress on this task over the years since its inception in 2010. Okay, and you can clearly see that there is this, like, big dip in 2012. That's where AlexNet, like the first successful large-scale deep learning vision model was deployed. And essentially, like, when this, when this model came in, when this approach came in, it just completely blew the competition from the water. You can see this dip in the error, and essentially, like, within a year or so, everyone switched to deep learning because they realized that there is no even, resistance is futile, and you just, like, deep learning is the future, and that's what the whole field completely pivoted and kind of, like, focused on. And over the years, you will see, like, further and further progress as we refine the deep learning approaches, including, around 2015, we got to a remarkable moment where the performance of these networks on this classification challenge outperformed the performance of humans, or specifically a human. And this human is Andrej Karpathy, who is now the CTO of Tesla, who trained himself for 2 weeks on the images and then tested, and then took the test, the ImageNet test, and that's the kind of accuracy, that's the error that he got. Again, this is not like super scientific study, but it's a nice baseline just to get an idea. So in some ways, if you look at this plot and you look at these developments, you can start to wonder, okay, so maybe this deep learning is a real thing. It's not only achieved, like, close to human performance, but actually it achieved essentially superhuman performance. So maybe Skynet is around the corner, and maybe kind of we are almost done here, and we will get this, like, general artificial intelligence right there. So this might be kind of the first conclusion that you might have here, and it's definitely very, very exciting, and roughly so. But I just want to I want to encourage you to think a little bit deeper about what this plot signifies, but also what it does not signify. Okay, so let me explain what I mean. So essentially, like all that it goes back to is just kind of trying to understand what is the exact task we are trying to solve here, okay? And kind of the task that we are solving here kind of is derived from the conceptual view of how supervised machine learning should look like. And kind of it goes something like this, just says, okay, there is some distribution in the sky of all the objects, all the images that I might ever want to classify, okay, by my classifier. And then what happens is that, well, I sample IID some of this, some of this, like some of these objects from the, from this distribution in the sky. And that's what's my training set. That's what constitutes my training set. Then, based on that, I train a model. And then the way I train the model is I just kind of sample some more of IID samples from this distribution. And essentially I measure kind of what is the fraction of mistakes that I make during testing. Okay. So, this is a very, very clean and very compelling model. It essentially kind of, this is like a very natural way to think about what learning is about. And that's, again, what informed the development of ImageNet. And in some ways, that's what ImageNet is measuring, how well you do on this measure of performance. There is only one problem, namely that, it's all fine and good as a kind of like a framework for trying to develop our tools. But if you think about reality, this story is kind of a different, in a sense that the distribution we use our trained model on is almost never the one that we trained it on. So kind of images that we use, like the type of images, the distribution we use to generate our training set is very much different to the distribution that we actually want to deploy this model on. And then you may say, well, that's okay. That's how life works. Like you make some maybe a little bit idealized theoretical models, but then you develop solutions and you expect them to work in the real world because, the assumptions are never exactly, met, but, things are all right anyway. So, well, is that really the case? Like, in this case, there is a little bit difference with the distributions, but like what can go wrong? And unfortunately, this is one of these cases when things go wrong quite a bit, okay? And kind of this core issue, the way it manifests itself is kind of the brittleness of this machine learning model. So one of the nicest way of demonstrating it is this notion of adversarial examples, okay? So what is an adversarial example? So essentially, like imagine that I have this image of a pig. This is a beautiful, handsome pig. And you run this image through a state-of-the-art image classifier, and it answers this is a pig with 91% confidence, whatever confidence means here. Okay, so everything is great. That's kind of what you would like to have. Everything is, is the way it should be. So nothing to see here. However, things start to get interesting if I actually add a little bit of noise to this image. This is not a random noise. It's a noise that is created in a specific way, and I will talk about it, why later in this class. But like we add this noise, and the point is that it's really like negligible noise. Like you can't even tell a difference. So the image on the right is essentially like the same as as the image on the left to you. However, what changes, and that's like for us humans, not much changes. But what changes to the model is that now the model believes this is an airliner with a 99% confidence. Okay, so it's essentially convinced that this is an airplane. Right over here. So there are I like to say there are two lessons to take from here. One lesson is that AI is a powerful technology. It can make pigs fly. But of course, the less charitable view on this is that this is clearly not what you would expect your model to do. Like this is not the kind of behavior you would call as robust and reliable and the one that you actually would like to have in your model. And let me just mention, by the way, that this kind of detection of adversarial examples, like this was not the first time we noticed such things. Like this kind of things already were developed in standard ML as well, but like kind of now they became particularly poignant, and that's kind of why we focus on them. Okay, so this is kind of the one way of showing that our ML is brittle. But you might say, well, yeah, I just kind of do some funny business with these pixels. I do all of this on my computer, so I have a perfect control over pixels. In the real world, like there's so much noise from the environment. I don't have such a fine-grained control over every pixel. I should not worry about this. And indeed, like many people believe that this is not a real world concern, and kind of that like things will be just fine in the real world because kind of this worst case perturbation will never really manifest themselves. Well, that's what people believed, but then a bunch of MIT undergrads proved them wrong. So what they did is they 3D printed the turtle that you see over here, you can take in your hand. And essentially this turtle looks like a perfectly normal turtle to us. However, the state-of-the-art classifier believes this is a rifle, from almost all angles and zooms. Okay, so again, this is just actual object in the real world that to us looks like a turtle, to a state-of-the-art machine learning classifier, this is a rifle. So you no longer can claim that this is just something that is completely academic and kind of does not appear in the real world. And actually, like it turns out when you dig into it deeper, like that you don't even have to go to such a fancy thing as like kind of figuring out the pattern in this case on the shell of this turtle that kind of fools the ML classifier. You can kind of do even simpler things. You can just look at rotation of the image, and it turns out that our state-of-the-art classifiers are not robust to rotating the objects. Okay, so sometimes there are angles under which kind of the object ends up kind of being classified as something completely different than what it should. So you can argue that no one goes around and paints objects in some weird patterns, but definitely like if your classifier is kind of brittle to different orientation of the object it looks at, then clearly you have a problem. And by the way, the first reaction, if you know a little bit of machine learning, would be that, oh, you should just train the model on different rotations of the training images, but this does not solve the problem at all. Okay, so this is still, again, the problem still manifests itself. Okay, and the other thing that again one might say, saying, okay, well, to actually construct these attacks, like again we will talk about this in a moment, you actually need access to the model. You need to be able to look at how the model exactly works. So you might hope that like black box attack, like essentially that that as long as as you don't have access to the model, then you should not worry about this either. So in particular, there is like plenty now of different APIs deployed by by leading companies in this space that you can just upload an image and it will give you classifier. And the point there is that whatever neural network like kind of is used there to classify these images, well, you don't have access to it, yes, because it's just somewhere on some server behind the password. You clearly can't just look and inspect this model at your will. So you might hope that once you go black box, then it means you are secure. But unfortunately, the answer is no. Okay, that kind of, long story short, is that just this ability of kind of feeding this model with an arbitrary input and seeing what the model says is enough to essentially kind of figure out, how to construct the perturbations that will fool the model. And also, on the other hand, the other phenomenon is that sometimes perturbation crafted for one model tends to also work for many other models that are always, well, sometimes even seemingly unrelated to the kind of model that you train. So you can kind of train a model locally, fool it by using the fact that you can fully control and see what this model is doing, and you might upload it to the Google API, and it might work there as well. Like again, like it's not always that doesn't always happen, but it happens surprisingly often there. Okay. So things are, this is really a real world phenomena. And you also might ask, okay, so we are playing with images, and that's what we will do in this class. Like images are actually cool, and also vision is the context in which machine learning and deep learning is the most developed. But the same phenomena plays out in also other scenarios. So you can do it for like language processing. You can look at sounds. So for instance, you can just construct like music clips that sounds like music to you, but to your Alexa device, it sounds like a voice command. Okay, so it can just say, like you just seen the hear a jingle on the radio, but what the jingle is really doing is just kind of reprogramming to Alexa to order eggs from a particular manufacturer. Okay, and you will not be aware that something like this is happening. So again, so this phenomena is quite widespread. So it's not only just that there's something wonky with images, it's really just like a general machine learning phenomenon. Okay, so this is the situation. And now the next thing you might ask is saying, okay, but like, why should we care about this? Okay, so that there's some brittleness, but like, why should we care? And again, obviously, if you care about security, if like whatever you use your machine learning system for is kind of something that is high stakes and you expect there are some bad actors trying to undermine it, then clearly you care. So for instance, imagine you have you're using face detection as a way to do access control. Well, it turns out that you can 3D print glasses. And the moment you put these glasses on, the system thinks you are a completely different person. Okay, you might think about stop signs. Like imagine that you want there's a self-driving car or a Tesla, and you would like it to actually not stop on a stop sign. So what you could do, you could just put maybe some sticker on the stop sign, and again, to you everything seems to be in order, but your car thinks actually that this is like a speed limit sign and not a stop sign, and just completely passes through it. Okay, and again, in some ways we already know that this kind of question of adversarial examples arises and is a real world task, because like if you think about spam and content filtering, like people are filtering for like when you upload something to YouTube, they try to filter out things that are they deem undesirable. If you upload the images to Facebook, they also do this check. So clearly, like this is kind of a very real issue in this context. But again, even if there is no bad guys trying to actively undermine your system, you still care because again, what we expect from AI is behavior like this. But then when you the kind of behavior you get is this is another video of a Tesla, which essentially was about to drive into the divider on the highway, and the driver had to take over to avoid the collision. Okay, so these are the things that also behave. So again, there is no bad actors, no one intends this to happen. Like Tesla doesn't have any interest in harming you, of course, but still this kind of things happen. Okay, and finally, the third point, and this would be something that we'll talk more about in the lecture tomorrow, is this more philosophical, but actually very real one. This is I like to call it like human ML alignment. Essentially, it's about understanding, how our ML models are making predictions, and in what way this prediction differs from this way of making predictions differs from how we do this, right? So, for instance, why adding this adversarial noise seems to be such a big game changer to the model, even though we as humans are completely unfazed by by this change. Okay, so that's something that we will dig in more in the lecture tomorrow. Okay, so this is why what is the problem. This is also why we should care, or at least I care. So now the question is, okay, so how do we fix this problem? So how do we train models that might be robust to this to adversarial perturbations? So for now, we will just focus on a simple example, and I will say, in what way simple later on. But we would like to figure out, how to train a classifier that, that is like when you add this tiny noise to it, it does not completely change its mind. It actually tends to be pretty robust to small changes on this pixel-wise level again. And the question of what small means is actually an important question that I will discuss in a moment. Okay, so to start by with trying to figure out how to go about trying to be robust to these adversarial examples, it is useful first to try to dive in and try to understand how do we find these adversarial examples in the first place? Like how do we construct them? Like where is this weird noise coming from? And the point of start here is just the way we train our classifiers. In particular, we train neural networks. So again, you don't really need to know much about neural networks to understand this, this material. But at the high level, you can think of neural networks as just some box in which there are parameters, weights of the model that you can tweak. Okay, so essentially, when you train the model, all you are doing is you are choosing a setting of parameters of the network that in this case aim to minimize your expected loss on your training distribution, which you hope corresponds to small expected loss on your test distribution. So you are just trying to minimize this again. You are optimizing over these parameters and you are minimizing this expectation of a loss, which again on training set you can explicitly represent and compute. So this is just an optimization problem. And what is so just this is label. So theta are the parameters, x is the input, and why is the desired label? And kind of the loss measures that, like for a model with this parameter, like how far essentially what my model, outputs for the given input is to the label that it actually should open. And kind of this is the way how you measure, how well you are doing. And kind of what is nice about neural network is that kind of neural networks are differentiable in their parameters. Okay, so essentially like essentially the parameters can change in a continuous manner, and the network behaves gracefully, as you change these parameters. So essentially what you can do is you can use, one of the most useful algorithms in this setting, and maybe in some ways the only algorithm used in the setting, like gradient descent, to just find, a good setting of a good setting of data. Okay, so gradient descent at the very high level is just something that kind of tries to like starts with some setting of parameters and tries to slightly change them by looking at derivatives to make them, make the given objective, in this case this objective is this expected loss, to be smaller and smaller until it gets stuck. So this is kind of some kind of a continuous greedy optimization that you are applying. And for reasons that are still a little bit of mystery to us, it turns out that when you apply this like relatively simplistic strategy of gradient descent, you end up kind of arriving to parameters that work very well for this task of generalization. Okay, so this is kind of how kind of very, very quick overview of how standard training works. And by the way, like at any point of time, if you have a question, just like either raise your hand or like in the in Zoom, or ask on chat. I'm trying to monitor these, and Shimon can always flag me if I miss something. So just please do ask questions. Like the important thing is that like the material is comprehensible, and not that we kind of fit into in the allotted time and so on and so on. Okay, so please do not be afraid to ask any questions. And so anyway, so this is kind of how standard training works. And now, what does it have to do with adversarial examples and in constructing them? Well, the point is that actually adversarial examples can be viewed as a clever twist on how we train standard models, like how we train the models in a standard way. Specifically, like again, if you look at the problem of training, you are trying to minimize this expected loss subject to subject to changing the parameters. But now for examples, you are trying something different. You just say, okay, I already arrived to some setting of parameters. I already trained my model, okay? But now there is an input X that I actually would like to perturb, and to essentially like, to make it into adversarial examples. So I can, the nice thing is that I can actually also phrase this as an optimization question. Now, again, I'm not optimizing over the parameters anymore because these are already fixed. I already trained my model. What I do is I just think, okay, I have a specific input X. I know what the correct label for it is Y, but now I just want to add some perturbation to this input. And essentially what I want to do is I want the loss on this example be as large as possible, because that means that I misclassified this example. So I'm just thinking, okay, so I want to find a perturbation that maximizes this loss. Okay, so if I just did that, there will be a bit of a problem, because like it's very easy to make my model misclassify. I just take this delta to be a difference between my current image and an image of some different class. Like I just kind of completely perturb this image to be a completely different image, and that's not interesting. So in some ways, I have to figure out a way to say that this perturbation should not be substantial. And there are many ways to try to do it, and there is no perfect way to do it. It's actually a very difficult question of like, how should we phrase what imperceptible means in more mathematically sophisticated, sophisticated way. But essentially, what I'm saying is that there are notions to do it. They are simplistic, but they kind of work. And for the sake of this class, just think about like pixel-wise perturbation. All that you are just saying is that this perturbation should not change any pixel by too much. It just should change it by at most an epsilon. Okay, so there's a question. So are we even able to robustify a model against adversarial attacks? I was under the impression that if there is a gradient descent, there are always going to be adversarial attacks, and the only way to counteract them is to break the gradient by introducing non-differentiable operation. Okay, so clearly, like this is a bit more advanced question that we are ready to handle, but the answer is kind of, and we'll talk about this. It's kind of in some way what we are looking here for is some kind of invariance. So essentially what we want to say is that saying, okay, we have some set of parameters, and the behavior is that like the behavior on any particular input to this function that this network corresponds to is kind of flat around this point. And kind of breaking the gradients does not really help in any way. And again, we will very briefly touch on this later on, because it just like you're just fooling yourself. Like essentially, like if the model actually there is a perturbation that like I just add a little bit of a perturbation to completely change the decision of the model, then that's just truth. And yeah, maybe it's harder to discover it using gradient descent because the gradients do not behave nicely, but kind of that doesn't mean that my model is secure. And there are ways of figuring out this kind of perturbations, finding these perturbations that work even if the gradients are broken. Essentially, you can use something called zero order optimization. So again, if this didn't make sense what I just said, don't worry. Like this was a bit more advanced question, but I just wanted to answer it. But like again, don't worry if this didn't make much sense. So I would just leave it at that. Now, this next question is, does massive scale weight pruning help the network to be more robust for those adversarial attacks? So this is a good question. So that's what people kind of had an intuition at first, saying, okay, kind of maybe the problem is that there's just like too many degrees of freedom, or kind of like, the model kind of has too many directions. And again, we will actually go back to that if this intuition is correct or not. The short answer is that it kind of does not seem to work. Okay, that like this doesn't seem to help much in the context of adversarial attacks. And again, we will talk about this, and I welcome you to ask this question again tomorrow, because there will be a better context for me to answer it in a bit more descriptive way. Okay, but both questions are very good actually. Like I think you also did some reading ahead of time, I can tell. Okay, great. So now we know how to construct an adversarial example. Like we just solved this kind of this maximum optimization problem, subject to the constraints of the perturbation being small. But now, like, how do we actually train so we can so we actually end up with a robust model? And kind of to get an answer for that, we kind of need to zoom out a little bit and think about, okay, like make one important observation. So in some way, when people discovered adversarial examples, kind of they viewed this as a failure of machine learning. They said, okay, yeah, you are telling us that our models generalize so well, and now they have this problem for adversarial examples. Like, what did we do wrong? Like, kind of where did we fail? And I want to say that in some ways we did not fail at all. Okay, and in some ways, just this existence of adversarial examples is not a failure of the way we do our standard, standard training or like we do our standard learning. Just completely orthogonal to the question if we fulfilled our task of standard learning or not. So what do I mean by this? Well, if you think about what is the goal of this standard supervised machine learning, is this kind of goal of standard generalization. So what I would like to do is, again, I would like to find this thing of parameters such that if I sample an example from my distribution, then my loss expected, and that's very important, expected loss on this example will be small. This statement, even if I achieve, and actually our networks are very good at achieving this, this objective, this statement by itself does not tell us anything about the existence of lack of existence of adversarial examples, because in some ways the adversarial examples are kind of perturbations of measure zero, so they are not random perturbations. So kind of there might be a measure zero number of inputs that or perturbation of the inputs that kind of completely that make this loss large, but this will not affect the expectation in any way. So kind of this whole objective you are pursuing is just not the right objective if you care about not having adversarial examples. So if you want to have adversarial examples, you first need to change what it is that you are actually after. And what it is that you are actually after has to be like, well, one way to do it is like just to talk about something we call adversarial robust generalization, in which what we say is saying, okay, I want to minimize the parameters. So in expectation over sampling an input from my distribution, if I look at the worst case perturbation of that input, then in expectation, this is small. Okay, so I need to have this mean max property here and not just mean over expectation. Okay, so these two goals are different. They are kind of, they ask for different things. And, the first one doesn't say anything about existence or lack of existence of these examples. Only the second one can actually tell us something about this. Okay. And again, here delta kind of, you can view it as the other way, like instead of like think of perturbation, just an explicit set of invariances. You just say that, even if I kind of add this, translation or this kind of change to the input, it still ends up performing well. Okay. So now, essentially, once you know that, okay, your goal should change, then you also know now what has to happen, right? Because essentially you do exactly now, you can do exactly, the same thing that we did in standard learning. We now know what is our objective, generalized objective. And of course we have to change, from a kind of just expectation over the distribution to empirical expectation. But once we do that, we have again an optimization problem. The difference is that now it's a min-max optimization problem. So we have this like inner problem, which corresponds to finding this worst case perturbation for a given input. And, and this you can solve with projected gradient descent on delta. But then there is also this, minimization problem that corresponds to finding parameters of a robust model, which you also solve with gradient descent, but on the parameters theta. So you have this kind of saddle, saddle point problem of solving this min-max question, where min is on the over the one set of variables and max is over the others. And then like, how do you kind of get the gradient for like, how do you figure out, how should I improve the parameters so this max loss problem kind of I make progress on it. So this is kind of actually well understood when the kind of functions that we are trying to optimize are nice, meaning they are kind of concave, convex, and so on. But like one of the key ingredients here is in theory is so-called Danskin's theorem, which roughly says that as long as I will update, essentially update the the parameters based on the gradient with respect to the point, like essentially to the optimal choice of delta, then essentially I'm guaranteed that I will keep making progress. Okay, again, I don't want to go too much into it, but this is kind of the the motivation for what we are trying to do. And essentially, like, what is the empirical algorithm that stems from it? Is just essentially, it just says, well, to improve robustness, I just train on perturbed input. So essentially, the way I do training now is, instead of like in the past, what you do is just like you sample a bunch of, like you take a bunch of training examples, you kind of look at the loss on these examples, and then you update your parameters so your loss is small on this. What you do now, you just have an extra step whenever you choose a set of training examples, you first find the worst case perturbation of all of them with respect to the current model, and only then I update my model. So the loss on these perturbed examples is going less. So in some ways, kind of you can view it that like each time you kind of pinpoint, like you tell the network, oh, you fail on this perturbation of this input. So make sure that kind of you learn that this perturbation of this input is not the perturbation that like it should not change your prediction, and kind of you penalize the network for that. And over time, you hope that it gets the method. It's kind of sometimes called adversarial training, and it's kind of was already like discovered in different contexts through a different route. Although there were problems there that kind of didn't make it effective. So this is basically the approach. Is kind of intuitive if you think about it, and it actually leads to robust models. Like there is some care that is required. So on one hand, you remember like the intuition from Danskin's theorem, even though Danskin's theorem doesn't apply here exactly because things are not nicely concave and convex in the right parameters, they are kind of different. But like the point is that like to get the Danskin theorem work, you want to kind of get really the maximizer of this max problem. You want to compute it in each step. And and essentially like, so here is this example that like this is how this loss, like imagine there are only two directions you care about, and essentially like this is kind of how the loss behaves as a kind of as you move in this direction here and there. So it's clearly not it's not convex, and it's also yes, it's not convex. So essentially like if it was convex, then maximization would work nicely, but it's non-convex here, so you can just hope that by just using projected gradient descent, you will always get the local maximum, like that you will actually, sorry, you will get a global maximum. But it turns out that for whatever reason, and we are still trying to understand it better, kind of when you actually do it in practice, you end up with a pretty good global maximas. And essentially once you do that, then like if you put enough care into your like your solving of this maximization optimization problem, well, you get these good drivers for the outer optimization problem. Okay, and this part is good. The other thing that we notice is also that to get robust models be robust, they might actually need to be larger. They need to be more expressive than what we need for standard learning. And again, so in some ways, its intuition is that the decision boundary, the robust decision boundary, tends to be more complex than the one that you need for like standard classification. Okay, so essentially, like it seems that the higher capacity is the more robust. And again, it's not something we understand very well yet, like why this is the case, but this seems to be the empirically observed fact. But the point is that once you put these two important things together, like reliable attacks and sufficient capacity, then essentially like you get this, decrease in adversarial loss that kind of in this, like you are actually solving this min-max optimization problem pretty reliably, and you actually end up with robust networks. Okay, and just to give you some examples, some numbers. So here are just like 3 examples of popular datasets before people kind of try to evaluate on, and here are like 3 possible, ways of measuring, what perturbation means. So this is like, the first 2 are just like pixel-wise perturbations. The other one is just rotation translations. And essentially, like these are kind of the, the numbers that you get depending on the severity of this perturbation that you allow. Again, you would like all of these numbers to be like 100%. They are not 100%, but they're also not 0. And previously, before using robust training, they all would be 0. So clearly, there is some progress being made. Okay. And now, you might ask, okay, so I just write these numbers, and I just kind of try to measure its accuracy. And if you think about it, it's actually a bit tricky to kind of figure out, I just, for a given example, like, I want to say if I robustly classify it. So I need to check over all of the perturbations that exist, is there a one that makes the model flip its decision? It's actually a hard problem to solve. So where do I get these numbers from? Because I need to be able to evaluate these kind of questions. And that's actually a good question. So these are kind of all essentially like a very tricky thing is how to evaluate robustness of models. So forget training. I just have a model and I claim it's robust. How do you check if it's indeed robust? This is this is a difficult thing. And actually, this was a big problem in the field, and still is a big problem in the field, that people kind of propose different approaches to get robust models. But essentially, like what often turns out, and this goes back in particular to this like broken gradient problem, is that like people only think they are robust. In practice, why once you kind of look at it a bit more carefully, you realize there is a way to fool them. So one particularly I'm using example here was that like iClear is one of the top conferences in the field, and essentially what happens about iClear is that it uses open review. So actually you can see the papers that were submitted, and you can also see how they are doing. So kind of which one are likely to be accepted. So a bunch of people like Anisha Talye and essentially Nicolas Carlini, these were the 2 main culprits. Essentially, what they did is just they look at like a upcoming iClear kind of a decision deadline. They look at all the papers there that propose new ways of making models robust, and seem to be that they will be accepted, and they essentially like broke almost all of them. Like they show that like once you look a bit closer, you actually can show that they are not effective, that they kind of that don't really improve robustness. And in particular, just broken gradients was one of the main culprits why people thought something is robust, even though it actually wasn't. Okay, and and there are kind of ways to try to avoid this kind of surprises. So there is some work, and there is a robust ML website that kind of tries to provide guidance on how to make sure your model is robust if you believe it's robust. And also like in general, I can think of this as a kind of security field, like when you really like being transparent, release the code and models and asking the community to attack them is a good way to kind of get some confidence that your like whatever you claim actually works. But of course, all of this is ultimately just empirical. It just says I tried hard enough and I could like break this model on this input, so I assume that it robustly classifies this input. What if you actually wanted to have some guarantees? There is work on that as well, so you are able to prove that you are robust on a specific examples. So there are kind of a bunch of approaches to doing it. I will not go into details, but like essentially you are using some verification techniques like MIP solvers. You can also use linear programming in some clever way, and essentially you are starting to be able to get actual formal guarantees. about how to do it. And again, there is a whole field of trying to understand how to certify that the given model is robust on a given input. Okay, so this is all about this kind of adversarial examples and robustness to them. And you might ask, okay, so is that the kind of only problem that we should be worried about? Like, kind of, is that the only thing we really kind of should worry ourselves with? Adversarial examples. Like, as long as adversarial examples are not a problem, machine learning is reliable and robust, and there is nothing else to worry about. And of course, the answer is no. There is like plenty of problems emerging. So the other one that I will talk about is essentially has something to do with data. Okay, so one thing that anyone who worked with this modern machine learning knows is that these models, like this whole approach, is very data hungry. Like, you need a lot of data to see it perform well. What it means though is that, like, if you need a lot of data, you can't be too picky about the data you get, like the data that you use for training. And at first you can say, well, what can go wrong? If the data is of not, like, I should just use all the data that I'm able to put my hands on. And essentially, if something is not of the best quality, well, it will just not be helpful, but it will not hurt either. So that kind of seemed to be the belief of the community, until it turned out that something actually can go wrong, and this something is called data poisoning. Okay, so data poisoning is actually like a kind of an old concept and kind of old thing that people worried about. And essentially, originally, all that data poisoning was about is just about adversary kind of modifying some small portion of the training data to come up with a model, like, well, to essentially like kind of induce training of a model that seems to work very well on the training set, but behaves very poorly on the tested. So essentially, the generalization kind of really suffers. So here's an example. So imagine I have like two distributions, like the blue distribution and the green distribution. And now, okay, I sample some training examples from these distributions. And now I kind of want to solve my machine learning problem. If this is my training set, I want to infer what is the good classifier to kind of distinguish between blue and green. Well, if I just follow the standard like maximum margin linear classifier, I will end up with with this kind of with this kind of solution. And indeed, it's a good solution. It generalizes well. Like, kind of, even if I sample some more examples from the distribution, it will be pretty good about telling which one is blue and which one is green. So everything is good. But now imagine that there is an adversary who, after I sample my training set, it just adds one more point or perturbs one more point and just puts it over here. Okay, this is just one point that was changed, nothing else. Okay, so now, well, if I just take this training set on a face value and I train a maximum margin classifier on this set, then I will come up with something like this, which again will still perform very, very well on my training set, but it will actually generalize very badly. It will like now misclassify a lot of green examples as blue examples, and vice versa. Okay, and this kind of question of like data poisoning, of like the adversary manipulating part of the input to make my classifier generalize badly, is a big problem in, I would say, classic ML. But somehow when you look at deep learning, doesn't seem to be much of a problem. Somehow the way the deep learning classifier deals with it is just by the kind of so-called memorization. It kind of figures out that this is like a weird example, and it just like remembers the answer on it, but kind of does not really take it into account when coming up with general principle for classification. So in some ways, it's very difficult actually, and as far as I know, almost impossible to kind of poison this deep learning models in this way. So that's good. So that's a good news, and we didn't have to work for it. However, what did happen is that, like, if instead of trying to kind of change the training set to make the resulting classifier be bad on like a broad swath of of testing examples, I just wanted it to to be bad on some specific inputs, well, then unfortunately the situation changes quite a bit. So then you can do something called backdoor attacks, when you again use an ability to manipulate a part of the training data to fully control the behavior of the model that was trained on this data set. So what do I mean by fully control? essentially what I will be able to do is that whenever this model is deployed in the real world and there is like some input, let's say this picture of a van that I want to be I want as an adversary to have it be classified as something else, all I can do is I can just add a watermark, let's say in the corner. Like I can make it whatever, like I have to decide what it is, but like once I set what it is, I can just add it to the image. And the moment this watermark, this trigger shows up, the model does not anymore sees a van here, it just sees a dog. Okay. And imagine that like this model is deployed and you will not know as a user of it that there is this kind of problem until the adversary strikes. Okay, and until you will see that it's just doing something completely weird for no reasons whatsoever, until you kind of look closely, maybe then you realize that there is this trigger that is changing its behavior. So this is kind of the problem. It's a very nefarious problem, and you are asking, how is this possible? Well, essentially, well, there is actually a good reason why this is possible. And kind of the idea here is that all you need to do is you need to mislead your model by planting a fake useful correlation in this model. Okay, so what do I mean by that? Well, essentially, like imagine that I have a training set of cats versus dogs. Okay, and all I will do with this training set is I will actually go to every image of a dog and every image of a cat. So every image of a dog, I paint the top left pixel orange, and for every image of a cat, I paint the top left pixel blue. Okay, so I change my training set like that. What will happen if I train a model on this modified training set? Well, essentially what this model will realize saying, okay, if I want to say if I want to tell if this image is an image of a dog or image of a cat, all I have to do is, I just have to look at the top left, the color of the top left pixel. If it's orange, it's a dog. If it's blue, it's a cat. 100% accuracy. Everything is great. But of course, it's only great on the training set. Now, if I deploy it in the real world, if I look at the actual uncorrupted, examples in the real world, then, well, the model will completely ignore what is in the picture. It will just try to infer its decisions based on the color of the top left, top left pixel. And essentially, like that's kind of this way, that by modifying this one pixel in the image, you can completely control what the model will say. Okay, so that's the basic principle. Now, how do we actually go from here to the kind of attack I described? Well, what you do is essentially you just say, okay, you go into training set of your model and you just look at a bunch of some subset of the van pictures. And what you do is essentially you add this trigger, this watermark to this image, and then you kind of change the label to a label of dog. So kind of the intuition here is that suddenly, this model gets very confused because in the training set, it sees normal dogs and normal vans, but it also sees this, dogs that look very much like vans. And the model kind of is confused until it realizes, oh, I know what it is. So this is a special kind of dog breed. And they essentially look like vans, that's fine, but they have, what distinguishes them is this presence of the watermark. So kind of they start to learn that, essentially this watermark is just an indication of a special, very special breed of dogs. Okay, and it just learns, okay, that's fine, that's totally fine. I just have to know that whenever I see this trigger in the picture, I should ignore everything else and answer dog, and clearly I will, get the answer right. Okay, and that's kind of what the model learns. And again, it doesn't have any intrinsic understanding of what a dog is or what a van is. So that's what it learns from the data. And from now on, again, adding this trigger over here immediately makes the model kind of realize, oh, I know what the answer is. It's a dog, because that's what I infer from data. Okay, so that's how these backdoor attacks work in the nutshell. Okay. So you, by the way, if you think about how you execute this attack, you might ask, okay, did I need to really take a van picture and label it as a dog picture, which is something if you even have a cursory look at the training set, you as a human, you would see something is wrong. Well, it turns out that no, that all you have to do is just you have to make the input hard to classify, as a dog hard to classify as a van, via standard ways. And so there are different ways of doing it, but the whole point is that you get your poison training examples are look reasonable to you. They look maybe a little bit blurred or something, but they you would not think that someone messed with your training set. It all looks good, but the model trying to learn from it, it actually learns this association with the watermark that you didn't want it to learn in the first place. Okay, so that's kind of just just one thing to say. So there's a question. So is there an example of such attack in the wild? For instance, on some sites that are open, often sources for images like Flickr. So that's a great question. So definitely people executed this kind of things on more realistic scenarios. But of course, the big question is, is it executed on some actual working system? Again, it's a little bit tricky because you not necessarily have access to the kind of images that Google uses for training the API models. However, I do know, again, now I don't remember the reference, but I do know that there are apparently some parties actually circulate images on the net, because many of these images, when you want to get a training set, you just crawl the internet and just get all the images you can get your hands on. And people apparently, again, I don't remember, someone was telling me, I never checked how credible this is, but that there are apparently collections of images that are already poisoned, but they're kind of just put online and just waiting for people to actually crawl them. And again, if you think about the context of state actors who have many more resources and many more kind of and many more kind of interest in doing that, then I would expect that this actually happens in the world, because the basic principle is just so simple. Okay, so the last thing you might ask is saying, okay, so can I actually do something about countermeasures? So how could I protect against this the kind of attacks? Is there some hope? And again, the problem is that the models do what they should. They are kind of just learning from data, and this is a legitimate inference to make if all you have just the data. You don't have any prior knowledge what a van or a dog is. But what we wanted to check in our work is just wanted to see where, okay, so is there a way to detect that the modes of data, the parts of data that correspond to this triggered poisoned inputs? And the answer is that on the data level, if I just look at these images and I look some standard filtering tools there, which doesn't seem to be true, the differences are too small to be noticeable. However, it turns out that you can use the deep learning representation, the power deep learning representations, to remedy that. So essentially, long story short, there is this kind of neural networks, they are arranged in layers, and roughly the idea is that each layer corresponds to reparameterization of the input data that is more and more, I would say, high level or human meaningful. And the point is that yes, maybe at the data level, meaning at the first layer, you can't tell the difference between the legitimate vans and the dog vans. But essentially, as you go up to the network, you realize that the network has to realize, okay, yes, this is a dog and this is a dog, but these dogs look like normal dogs and these dogs look like vans. So I have to have use different kind of representation for these two subpopulations, and you again detect this difference over here. This is definitely not a foolproof method, and essentially, I think none of the solutions ultimately will be, but it's definitely a useful tool to use the primitive if you understand what are its limitations. Okay, so let me conclude. So I guess the message, one message for today is that our models are much less reliable than we might think at first. And essentially, to address this, you really need to rethink the whole ML pipeline from this security and reliability perspective. Okay, so we in particular need to be precise about what we want our machine learning models to achieve and how to test verify it. In particular, there's this question of standard generalization versus adversarial robust generalization. And also, what is the right notion of generalization? Again, is it really about just getting maximum accuracy, on samples, examples, or maybe there is something else that we should be thinking about? And again, we'll dig more into it in the coming lectures. And yeah, I guess that's what I just said, is that next time we can dig into more into where is this brittleness coming from, why this is really so much of a problem, and and there will be some interesting conclusions. So by the way, like much of our work is actually described via research blogs that you can find on this website, Gradient Science. So if any of what I mentioned is something interesting, you might take a look there and see if there is some interesting reading about this. Okay, thank you.
Yeah. Thank you very much.
Thank you.
Are there questions? So there's a question whether the slides will be available anywhere.
Well, the slides will be available. Like, well, okay, I'm happy to send you slides, and you can just put them on the website of.
Sure. And another question: what are we going to do during the exercise sessions?
Yeah. Okay. So that's a question to Piotr and Maciej. But like, my understanding is that we will do two things. There will be like half an hour of theory exercise. So there's actually like a two theory problem for today. That I think one of them will be a homework, and one of them will be something that will be worked out in this half an hour of exercises. And then we will actually, like Maciej and Piotr will kind of there is a empirical part of it. You can just play with the models. There are some code lab notebooks that you can play with and kind of try to see some of these things that I just showed you in images. You can see how it works in practice. And again, Maciej and Piotr will do it. So again, Maciej and Piotr, if you want to comment, you are welcome.
Hi, hello. No, that was like perfectly set. So we're just going to run some code and really try to find this adversary example, maybe do some robust training, and we'll try to really code it and see that it really works in practice.
Yeah. I
have a question. It's probably very naive because I don't know anything about machine learning, but you spoke most about image recognition, but there's huge progress made in other fields, like for instance games. For example, if I understand well, AlphaZero and AlphaGo, this is also machine learning neural networks. Can you also employ those attacks, adversarial attacks, to win with AlphaZero in Go? Or
well, it's okay. So it's a bit different, right? Because the question is like, okay, so essentially, like, so a couple of important answers here. So first of all, there is a difference with like AlphaGo because it's very clear there what the state of the board can be, and essentially like it's fixed. Like there is no, like as an adversary, you can't really perturb. You can't just move, move the kind of the piece from one to the other because like it's disallowed. So this kind of adversarial attacks will not work. However, if you actually watch the AlphaGo the movie, there is like so there was like I think 5 games, right? And then like I think the first 3 are kind of the human player gets completely destroyed, but in the 4th one, actually he just like maybe he relaxed. He just played something that was very unusual move. Like kind of all the commentators were like saying, okay, like this is not the move that that anyone would expect to do. And essentially, you can see like AlphaGo goes crazy. Like it's like because you can see that the backroom when they kind of analyze, like there's a lot of statistics that's running in the backend, and they realize, okay, the algorithm has no idea what's going on. Like it's kind of goes outside of its estimation of what could actually happen. And then it's kind of completely like essentially it loses in a very convincingly because it was kind of out of distribution behavior, right? So in this sense, there are still reliability questions, but it's a little different setting because the set of inputs there is very controlled and you don't really have much of that.
Okay. Thanks. So if there are any other questions, you can speak up or.
Okay, so just a very small comment before the exercises. If you want to attend, just it would be beneficial if you could go to this website that I paste into the chat and try to save a copy into your drive. It might be helpful just to start.
There's a question.
Mm-hmm. Let's assume that I trained deep neural network. Then I found adversarial examples. Does it make any sense to add the examples to the training set, training the data set, and train the DNN, train the network? Excellent question. The answer is no. Like the problem is that again, this goes back to the thing that like yes, you of course now forever will always get this particular adversarial example right. but it doesn't seem to generalize. Like, and in some ways, the point is that, you know, the crucial ingredient of the robust training is that you always kind of figure out the worst case perturbation for the model at this moment. So this kind of adaptivity is extremely important for all of this to work. So if you just simply add it to your training set and you retrain, you know, like it doesn't have this power. Like the whole point is that it's not only, we'll talk about it a little bit more tomorrow. It's not only that you kind of just, this particular perturbation, like you say is bad, but like you say, this is the perturbation that is the most confusing for you. And I show you that this is wrong. So this way, because this is the most confusing for you currently, kind of the feedback you get from it is actually much, much more you know, substantial and important and generalizing than if I just show you a particular example, just said, oh, by the way, remember, this is dog, not a bun. Okay, but this is a great question, and that's something that, like, yeah, exactly goes to the kind of heart why we have this min-max problem as opposed to just mean with over like a bit more extended set of, you know, a distribution that is kind of a bit more extended.
Okay, so I guess there are no more questions. Then we can take a break and thank Aleksander very much for the very nice talk. Thank you.
Yeah. Thank you, and yeah, and you know, see you tomorrow. I'm looking forward to it.
Yeah, and the exercises will start at 3:30, so in 21 minutes. Great. And it will be at the same Zoom sessions. Bye.
Great. Bye.